Hey everybody, today we're looking at free fall. So hopefully by now you've read through the notes. There's definitely some good key points in there. I'm going to hit the highlights here. This is more kind of for the math side of things, but definitely read through that first, and then hopefully this video helps as well. But topic of free fall. So we're either dealing with an object that gets dropped, an object that gets thrown straight up in the air, or something that goes straight up and then comes straight back down. So we're still in one dimension. It's just our one dimension is now vertical instead of horizontal. The kind of the nice thing is our equations for this don't change. So if you've been using the equation board a lot, these are equations number 2, 3, and 4, which should look really familiar. We've used them a lot. So those are still what we're going to use. We won't use equation number 1. If you remember, it's just velocity equation. It doesn't involve acceleration. And if we have an object that's in free fall, it most definitely is accelerating. So that's just something to keep in mind. The one big change, if you want to call it a change for these equations, is basically now, if objects are in free fall, we know the acceleration. And if you look at all of these, there's acceleration, there's acceleration, there's acceleration. If they're in free fall, we know that the acceleration due to gravity is 9.8 meters per second squared. So we put the negative sign. I'll show you why here in just a second, because it's in the downward direction. Not that it's a negative value, it's just a direction. The down is the negative direction. And so any place in these equations that you see A, you can plug in negative 9.8 meters per second squared for that value, assuming that you're on Earth. There's a few problems you'll work. If you go off of the planet Earth, if you go to Mars, or the moon, this value changes, and so you would have to plug in a different number for A, or sometimes I have you solving for what like the acceleration due to gravity on those planets or moons might be. So just keep that in mind. Most problems you just assume are on the Earth unless the problem states differently. So you'll be able to use this. So in a way, it almost kind of makes these a little bit easier to use because you know what you're going to plug in for A. So keep that in mind. We talked a lot in the notes about the value of G and why it's this number and that sort of thing. So definitely review those slides as well. Also, as we go through the notes on this, we kind of draw a couple arrows just to kind of get our bearings because there's going to be some key information that we can write on these arrows. So up is considered the positive direction, which I think makes sense in our brains. Thumbs up, that's a positive thing. Down is the negative direction. So values of things on the way up are positive. Values of things on the way down are negative, just based on the direction. So if something's thrown upwards, its displacement, we will consider that to be positive. Its velocity, we will consider that to be positive. The one exception is its acceleration, because this is its acceleration, and we've already said in the notes, and we've already kind of talked a little bit about it here, that because it's negative, it always acts down towards the center of the Earth. It's always down. And so the acceleration, even in the upward direction, is negative, because gravity is always in the negative direction. Over here on this side, since down is the negative direction, acceleration still works downwards because it's pointed towards the center of the Earth. Velocities that are heading down will now be assigned a negative sign because of the direction. And then same thing, displacements on the way down, negative. So our negative direction and our positive direction. From the notes, there was also one key thing, or a couple key things, I guess, in terms of helping you set up some of these problems and figuring out some of the variables that might seem like they're missing. If you have an object that's thrown straight up in the air, so here it is, on the way up, it's slowing down because gravity's slowing it down because gravity's working against its positive velocity. It's going to slow down, slow down, slow down, and then right as it gets to its highest point, it actually stops before it starts to fall back down. And so if you're just looking at something that's thrown straight up into the air, we can actually look at this point right here, and we can say that the final velocity of that object is 0 because it comes up and stops before it comes back down. A lot of times that piece of information will help you fill in. Like if you look at this equation, right there's a VF. Sometimes that value is going to be 0 if it's up here at the top of its flight path and it stops before it comes back down, or if you're just looking at the trip on the way up. So keep that in mind. There's another VF that could be 0 depending on what's going on in the problem. And then Another piece is if you're dropping something. So let's just say something's in a window, it falls out. Its initial velocity right here, right before it falls off, it's not moving. And so you can actually label that if we're over here on this arrow. The initial velocity of something that's falling is zero also, because look at it, it's stationary and then starts to accelerate and go faster and faster in the negative direction down towards the ground. So if you're dealing with a falling object, a lot of times when you're looking at these problems, there's initial velocity, there's initial velocity, there's initial velocity. There's a chance those could be zero if the thing is just being dropped. So a lot of times you have to read into the problem, figure out what's going on. Sometimes you won't see an actual number. You'll just have to say, oh, wait, okay, it's dropping. It's starting from rest. I know VI has to be zero. So keep that in mind. That'll help out for sure. Another thing we could label here, if you think about this, the amount of time that it takes to get to the top of its flight path is identical if we're having something that's going up and coming back down. The amount of time it takes to go up is the exact same amount of time that it takes to come back down. That's because the acceleration is the same, right? So it's always negative 9.8 meters per second squared. So it's going to travel the exact same distance on the way up as it does on the way down. It's going to be accelerated at the exact same rate on the way up and the way down. And so that means the time that it takes to go up is identical to the time that it takes to come back down. So a lot of times I just put a T here equals T, just kind of meaning to say time up equals time down. Last thing we can say is down here. Let's say we throw a ball up, if we're throwing a tennis ball or something like that up into the air, and let's say it has an initial velocity down here that as it leaves our hand of 5 meters per second. I'll label that VI down here. So 5 meters per second, it's going to go up, stop, come back down. And as it comes back down, it goes faster and faster and faster and faster until it gets right back to its starting point, which I guess would be your hand. And right before it would hit your hand on the way down, it will still be traveling, or I guess at that point, it will be traveling again at 5 meters per second. The only thing that changes is if we're dealing with a velocity, is the direction will be negative because it's on the way down. So over here, we could label this as the final velocity as that thing comes back down. That will be identical to the initial velocity that you threw the ball with. So we're talking 5 meters per second, and this would be in a downward direction, and this would be in an upward direction. So those kind of show you, I guess, the relationship between initial velocity and final velocity. If the ball goes up and comes back down, those velocities will be identical. So I think that's about it. That's the run through. Try some problems, and then, of course, let me know if you have questions.